So I'm here to talk about some of our advances in our material selections for our LEC and EDIC. And so as Frank just showed here, here is a kind of layup of our plane parallel gaseous electrolyte EDIC, or LEC. And here we have our composite working electrode, or emitter, and our collector counter electrode. And then we have our active area of our hydrogen-included hydrogen host material that makes our composite working electrode the composite. And here's just kind of an example of one of our pressure vessels that we use for testing. And just kind of a little bit of housekeeping here of our testing procedure at the time when we were running some of these tests that we're reporting on. Our pressure vessel here, we can take up to a couple bar of pressure. We can accommodate 2 cells at a time for testing. And essentially we'll just take your cell, connect it to the internal leads. You can, if you're doing 2, we have a separator that we put in to keep them from electrical contact and also from electrical contact from the sides. We then take our vessel and we run extended vacuum on it. And the reason we run the extended vacuum is because water is not your friend. So you really have to do a hard vacuum. And then we will refill and back and forth several times. After we do that, the cell is usually not very happy. So we put it in the kiln, then we put it about 25 to 35 degrees Celsius, and we wait for it to recover. And this can be a few hours, up to 8 to 36 hours to several days. And if you go higher in temperature and try and push the mobility of the ions higher to try and get more flux of the hydrogen deuterium in, it can stunt the cell from there on. So you do need to kind of be careful in how you bring it back up. And here's kind of an example of this. Our cell is in the kiln here. And hopefully when you're assembling the plane parallel one, you happen to capture the surface area that you put on for your active material. We record temperature as the floor temperature. We have a thermocouple on the floor of the kiln and also an air temperature. And we take an average of that. We don't currently have a thermocouple inside the pressure vessel. And then you measure the voltage that's coming out. And while we're waiting for it to recover, we monitor the open circuit. And then once it finally appears to have stabilized, the kiln has stabilized, you do your initial load test. And so you start from 1 megohm and step down. And you go all the way down to 10 ohms. And you record your data and decide what new power level you'd like to go to and what temperature, and wash, rinse, repeat. After you do your testing and collect your data, this is what I call our first look data processing, where we record the cell number, the date, the time the test was run, what was the build of that cell, what equipment we were using to test it with, and then we just record our voltages versus resistance, and then do some basic calculations of the current, the power per area, and our shunt current. So this is a pretty typical LEC cell performance characteristic shape for a LEC. So you have our voltage on top, current, power is the yellow, and our power density per square centimeter. All right, and so one of the things to note is that there are several operating regimes of the LEC. So at open circuit, you have the cell's contact potential difference, and that is your drift regime. At the bottom end of resistance, you have your diffusion regime, and in the middle where they meet, you actually have the power regime where you can reach peak power. All right, a little bit more housekeeping on an active LEC cell. So in this case, you can see our composite working emitter electrode and our active material here, which is emitting the electrons, over towards the counter electrode here with our very fine pore capacitor paper. And you can also see our space charge here. Space charge only occurs when the current density becomes very large, so that's more towards your contact potential difference. This is a slide just to kind of encourage you to do a full load test at a bare minimum. As you can see, the very unusual behavior on the low end. We'll comment more on that. It's a very complex system here where we were employing some techniques to try and push the cell further and get more out of it. All right, and here's a more interesting cell that we had. We were testing a cell, and this is a nickel cell where we're using a nickel particulate. And we hadn't really used a nickel particulate because all indications were that nickel needed to be hot. And so we had essentially avoided using that as something for co-deposition. And initially, when we started testing the cell, it was a very puny cell. It was not very active, didn't work very well, struggled to get down even to under 100 ohm in resistance. Just did not work until it did. All of a sudden, it kicked off. And as you can see here, from here, all of a sudden, something happened. And we knew something was happening, but we weren't quite sure, so we went and did some data processing on it, that first look. And we're like, we graphed it and looked at it, it's like, whoa. So we went back and we looked, and it continued on for about 34 minutes through the next test. All right, next one. All right, so as I said, in the previous slide, we mentioned that the work function of the composite electrode is actually going to be lower than the counter electrode. And so here's just a quick calculation of the estimated work function of the composite electrode when it's active. And indeed, when you use our numbers from here, from our current, we get a work function of 0.66 from the emitting electrode. And we get a current density of 1.83 milliamps per centimeter squared. All right. And just so additional curiosity, we were wondering what the activation might be. So we plotted some of our data, and here we have the voltage at 47 ohms across 3 different temperatures, I believe 25 degrees Celsius, 43, and 66. And the question is that exponential? It may be. So we went on and checked, and we're looking to see if we have our nice little relationship of the slope in a linear line here. And so we plotted our data and calculated that out and did a regression, and as you can see over here, and that's kind of the fit. And the regression has a value of 0.864, which is not bad overall. Especially for something that is nonlinear. So that's a little bit interesting. So that's kind of showing us that yes, it is exponential, and so let's go ahead and calculate our activation energy. And at that, so here's kind of just a derivation of what we're doing, the 2-point activation energy. And so at the 47 ohms, we ended up with a activation energy of 0.92 electron volts for the activation energy at. All right, and so our cell was not working very well until it was working well. We had this excess activity event, and during that time, the cell of magnesium capacitor, our nickel particulate, and nickel, the cell sustained this excess activity, and it was observed for the hydrogen-included host material at a 65 degrees Celsius. One of the possible explanations is that there was an increase in ionization of the gas due to the last enabled nuclear reaction activity event. And it is interesting to note that after this event happened, the cell worked much better at all temperatures that we tested it at. It had no problem getting into low resistances. And that's, so in summary, the electrodeposited nickel and its particulates can now be considered a low-cost alternative to hydrogen host materials for the implementation of ELEC or EDIC at temperatures less than 150 degrees Celsius. It now joins iron and palladium and titanium as particulate candidates for HHM material. And so when you take precautions as Frank mentioned, it's incredibly easy to make an electrochemical battery. So if you take some precautions, especially with the plane parallel style LEC, you have to take precautions to make sure that you don't get chemical reactions. It offers low cost, nickel is now a low cost alternative to some of the other materials such as the palladium for ELEC implementation. And activation energy and work function have been shown to be less than 1 electron volt, and cell operation has been shown to work at temperatures less than 150 degrees Celsius, in fact, much less than 150 degrees Celsius. And I just want to thank the people here at IWAM, and I also want to acknowledge Dr. Alan Smith, who has worked with this for many years, helping to develop, giving a lot of input, and he did some work to ensure that IWAM stayed alive. I just want to acknowledge and remember him. So, all right, and thanks for your attention.
So, any question? Yeah, that question, see.
Okay, according to you, which one can be the extremely low work function materials that make such wonderful result? Just guess. Everything is okay for me.
As far as the active material, what makes it such a low work function, what we're finding is...
Sorry, I can speak slowly. I am Italian.
what makes the composite electrode the low work function electrode, it's actually the active area of our active hydrogen-included hydrogen host material. It is actually the included material that causes it to be the low work function.
But which kind? Nickel, powders, or iron? Do you have some idea? Maybe.
Well,
even sun, it's okay. Just
they all work. I'll put it this way: they all work, and you will get less than 1 electron volt for the work function difference when you actually have active material, and that's actually a way to validate you have a real active cell. That's not the battery. The work function goes down dramatically. Frank has something.
I want to answer.
Yeah. One of the puzzles or riddles that Richardson is he used the same materials. He did not, so the work function was very, very low. And so that's one of the series of tests we're doing now. We're using nickel for both the anode and the cathode. And in one case, we have the active material, and so the work function actually drops because of that. So at that point, the high and low work function can change, which may explain why we actually see the change in sign over our cells over time. So we have a lot to learn to present at ICCF27.
Okay.
So when you talked to me years ago and I was suggesting that there might be other approaches, it was clear that this kind of process might occur, but it was also clear that the work function would be really low. Oxides have low work functions. The metals have much higher work functions. You can have some oxides, which are known, which have sub 1 eV work functions. But I was thinking that in your system, there might actually be a different modification of the mechanism. If you had a molecule that carried your charge away, then it would sort of work similarly, but that would give you a way to get a low work function. So if you had a molecular anion come off the surface, that would give you a way much more easily to get a low work function. I don't think that you're going to get a low work function from oxide on your surface here, but maybe.
I think that's one of the treatments that they use for the capacitors, is they actually oxidize. And aluminum, it's hard to get aluminum that isn't oxidized, basically. So as I mentioned the other day, we talked earlier and kind of had a resonance. So we need to work together for our paper for ICCF27 and hopefully answer some of these questions.
So now you're using something which is high vacuum system. Are you planning to go to something like a UHV growth of films, or going for more surface control experiments?
I'm not quite understanding the question. What? Yeah. Yes.
We have more ideas than we have time at this point.
Yeah.
Okay. Any more questions? So, anyway, thank you very much for your time. The next.